Welcome back. This again is Honors Geometry Unit 6A, and we are in Section 2, Arcs and Chords of a Circle. Today we are going to find lengths of segments in circles and also identify and name the arcs of a circle. So we're going to start with the types of arcs. We've got minor arcs and, well, actually, an arc is a portion of a circumference of a circle. Okay, or sometimes referred to as a fraction of a circumference of a circle. And so arcs can be measured in degrees and they can also be measured in length. And we're going to do both, but we're going to just start by thinking about the degree measure of arcs. And so let's start with minor arc. So a minor arc is going to measure between 0 degrees and 180. And the way we write that is 0 degrees is less than x, which is less than 180 degrees. Okay, so a minor arc is basically it's less than a semicircle. So some examples of minor arcs could be like here, arc BC is a minor arc, and arc FE, that's a minor arc. So anything that's less than less than the semicircle would be considered a minor arc. Now when we write arcs, we have to use this little arc symbol. So like I identified arc BC, and I also identified arc FE. There are others on here, okay? And so this is what we would consider. Usually minor arcs are labeled with just 2 letters, okay, which is different than major arcs. Major arcs are going to measure between 180 degrees and 360 degrees. So 180 degrees is less than x, which is less than 360 degrees. So this time it's an arc that's actually bigger than a semicircle. So if I look at a couple examples of arcs that are bigger than semicircles, so let's say I do this. Maybe I go all the way around like that. So that arc covers a lot of different points. Okay, now we definitely, when we name that arc, we want to use the endpoints F. We want to use F and D. But then you could pick any letter in between to show that you're going from F to D through that letter. So for example, I could call this arc FAD. Okay, because we start at F, you go through A, and eventually you land at D. So we'll use 3 letters with the first and the third being the endpoints of the arc. So there's one example of an arc. Okay. That's a major arc. We could do another one. Let's try. Let's say we do, this will be like a big one. We'll go from, D all the way to C like that. That's a big arc as well. So if I was to name that arc now, again, I could start with D or C. Let's just say I start with D. Okay, and I have to end with C, and I could pick any point in between. Let's say I pick B. So arc DBC. That's another example of a major arc. So major arcs are typically written with the 3 letters. So semicircles are arcs that measure exactly 180 degrees. And so here, let's use exactly 180 degrees. And so when you name a semicircle, I see it, 2 ways. Sometimes I see it just written like, CF. So start at, C and go to F. Like I'll see that with just the 2 letters. So arc CF, okay, no matter which way you go, C to F, you're going to be referring to a semicircle, okay? But I've also seen it written with another letter in between it, like CEF, perhaps, something like that. So that's another example. That's an example of a semicircle. On the next page, we're going to practice naming some arcs. Okay, so we've got our circle, S over here, and they want us to name some arcs. And so to do this, there's probably lots of arcs we could name, but I'll just pick out a couple. So one example of a minor arc could be arc RO. Okay, so I see this one right here. There's arc RO. I could also pick maybe arc, pick a different color, and we'll say maybe arc, NU, like that. So there's another minor arc NU. And, maybe DN. That's a minor arc. So those are just 3 examples. There are others on there. Now some major arcs, remember these have to be bigger than the semicircles. So if I want to do some major arcs, let's say I do How about D-U-N, something like that. There's an example. So D-U-N. And let's try a different one. How about I try arc? How about R-U-D? We'll try that one, R-U-D. There's a major arc. Again, something bigger than a semicircle. Let's try one more. Maybe I start with U and I go all the way to O. So maybe we'll call this URO. And that would be another example of a major arc. So these are big arcs, bigger than a semicircle. So to name our semicircles, we could just use 2 letters or 3, but I'm going to use 3. So let's say RDN, there's one of them, RDN, and the other side maybe RUN. There's the semicircles. Okay, so what we're going to do now is we're going to be starting to work on different angles and their measures with respect to their arcs. So we're going to talk about intercepted arcs quite a bit. And so an intercepted arc is the part of the circle we say is cut off. Sounds kind of funny, but we say it's cut off by an angle. Okay, so here are examples of intercepted arcs. So you'll see, this is an intercepted arc for that central angle right there. And, this is an intercepted arc for that angle. So you got these different arcs, like here's a big one. That's a big intercepted arc. Okay, and so the arcs and the angles are going to be related to each other. So we're just going to get familiar with looking for those intercepted arcs for those specific angles. Okay, so let's practice that here. We are going to answer some questions about some arcs that are cut off by an angle. So we're going to find the angle BDA. So when you do BDA, so there's B, there's D, there's A, it's going to be arc BA or AB. Okay, so that's what we mean by cut off by the given angle. Okay, EHC. Let's do that one now. EHC, CE is the arc. Let's try FAD. FAD. Here's the angle, which means the arc is FD or DF. The order doesn't matter. Now let's look at FAB. So here's FAB. That's going to be a really big one because that's going all the way from F to B, which means that's a major arc. So probably going to use a third letter here for angle FAB. I'm going to go with like FDB. Try that. So that's going to be a bigger one. Let's try ABD. That's this one here. ABD. It's another kind of big one. It's going to go from D to A. So I'm just going to use DFA. Use DFA. And AFB, let's look at that angle. AFB, that's kind of a little one. AFB looks like BA. So notice BA was used twice. BA is actually an arc that's been cut off by 2 different angles. Like if you look at part A, BDA cuts off that arc and AFB cuts off that arc. And these 2 angles are both the same type of angle. So we're going to learn what's true about those. You can kind of predict what might be true about angle F and angle D. All right, time for you to try a problem. You're going to name an example for each of the following in circle S below. So you can pause the video and spend some time naming. And please use good arc symbols. Okay, so hopefully you're back and we are able to go in and put down an example for each of these. So for minor arc, you could have listed a lot of different things. I'm just going to list EG. It's kind of a tiny little one, EG. That's an example of a minor arc. For my major arc, I'm going to use OGD. That's a pretty big one. That goes all the way around like that. So I'm going to use that one, OGD. For my semicircle, I'm going to use ODI. And the intercepted arc for GSI is GI. That would be this one right here. Okay, so we're going to kind of switch gears now, and we're going to start working on some problems that involve some segments inside the circle and just some distance. So we're going to first identify what they mean by distance from the center of a circle to a chord. We're going to identify what we mean by that. So the distance from the center of a circle to a chord is, it's actually the length of the perpendicular segment. So it's the length of this segment right here that forms a perpendicular. That's what we call the distance. Because, I mean, you can draw a segment from the center to that chord in a lot of places. You could draw it there, you could draw it there. Okay, but those are not considered the distances. So I'm going to erase those. Let's just undo. There we go. The actual distance is referred to that segment that's perpendicular from the center to the chord. So it's the length of the perpendicular segment from the center of the circle to the chord. Okay? So that's what we call a distance. When they ask you to find the distance from the center of a circle to a chord, they want you to draw that perpendicular segment. Okay. Now the next theorem is what we call a radius chord theorem, and this one says that if a radius is perpendicular to the chord, so if a radius is perpendicular to the chord, then it also does something else special. It actually bisects the chord, and bisects, remember, means divides it into two equal halves. So if your radius, okay, so you can see our radius is right here. If your radius is perpendicular to a chord, it divides the chord into two equal pieces. Okay, so kind of get used to that picture. When you see that right angle there, that means you've chopped that chord in half. Okay, two equal pieces. And then there's some problems that go along with these theorems. Suppose a chord of a circle is 16 inches long and is 6 inches from the center of the circle. Find the length of a radius. Okay, so we have to figure out where to put everything. It says, suppose a chord of a circle is 16 inches long. You can draw that wherever you want. I'm just going to go ahead and draw it right here. Like, there's my chord. It's 16 inches long. I'm not going to put that 16 in yet because I know that it's also 6 inches from the center. Well, distance from the center is that perpendicular. That is 6. And because I drew it perpendicular, that's going to take that 16 and divide it into 8 and 8. Okay, so you got to kind of put those together that way. So that's the given information. We got a chord that's 16 inches long. It's 6 inches from the center. That distance divided that chord into two equal pieces. And the question is, find the length of a radius. So we actually need to find the radius, which I'm going to draw it right here. Or, you know, you could draw it right here, wherever you want to draw it. And that's going to make a really nice right triangle on either side, which means if I need to find that, let's say I let that be x, I can set up Pythagorean's theorem since that's a right angle. So I can do x squared equals 6 squared plus 8 squared. Or x squared equals 36 plus 64. X squared equals 100. And x is the square root of 100, or 10. And so our radius is 10 inches long. So in problem 14, they might give us different information. Okay, so let's see what they give us this time. It says find the length of a chord. Find the length of a chord. So we don't know this piece. Okay. But we do know it's 5 inches from the center of the circle. So I'll put my 5 there. And if it's a distance, it's a right angle. And they gave us the radius. So the radius is 13. Let me draw on the radius again. The radius is 13. I'll just draw it on one side this time. They want to know the length of the chord. So if I find this piece here, I could just double it. So let's do Pythagorean's theorem again. This time I know the hypotenuse. 13 squared equals 5 squared plus x squared. 169 equals 25 plus x squared. Take away 25 on both sides, and we're going to get 144. So these come out kind of nice. Equals x squared. And then the square root of 144 is 12. Okay, but remember the chord has been divided into 2 equal pieces. So it's actually 12 and 12. So I can put those in there like that's 12 and that's 12. So that means the chord is actually 24 inches. So now we have a U-try. So for number 15, it says a chord measures 24 centimeters and the radius of the circle is 15. This time you want to find the distance from the chord to the center of the circle. So I would say pause the video, see if you can get the picture drawn, and see if you can solve for that distance. All right, well, hopefully you got a chance to draw the picture. Let's go ahead and do that together now. So we're gonna draw a chord. I usually draw it in the same place. It's 24, but I'm not gonna put in 24. I'm actually gonna wait till I draw in the distance, and then I can make it 12 and 12. And they also tell us that the radius of the circle is 15. And so what they want us to find is the distance from the chord is from the center of the circle. So I'm going to put my X here. So we can set up 15 squared equals x squared plus 12 squared. And then calculate 225 equals x squared plus 144. Oops. X squared plus 144. And we can subtract 144 to get 81, which means 9 is equal to x. So that means that our distance is 9 centimeters. All right, that is actually it for section 2. So again, if you have any questions in class, please make sure you ask your teachers. Have a great day.